Hey, welcome back. This is Jeff Disher again. Today I'm going to be talking about the first in sort of a sequence of videos which were based on something someone had actually requested, which was they wanted to know how CPUs actually physically execute instructions, like how the actual hardware works, what it's connected down to, and how's the program mapped down to that. Now this is of course a really huge area that requires a lot of background knowledge to actually explain that. So this is going to be the first step in that. In this one we're going to be talking all about Boolean logic. Generally speaking, this is kind of part of the overarching concept of Boolean Algebra, which was something which was developed by George Boole back in 1847. Of course, he didn't call it that at the time, but anyway, that's something this is sort of the broader ideas behind it. Boolean logic is really more about a specific way of looking at it. The term is more likely what you're going to hear when people are talking about building circuits and things like that. The main thing to realize about Boolean logic is within that system, everything has one of two values. It's either true, or 1, or false, or 0. And all statements are based around combining things which could be 0 or 1 into a statement which could be some combination of those to an output that makes sense for whatever you're trying to do. The three basic operations you can perform within Boolean logic are, first of all, conjunction, also known as AND. And this means that you can say, okay, if X and Y are true, then the result is also true. Now that means that if either one of them is not true, then the answer will be false. The second one of these operations is disjunction. This is what's often called OR. So in this case, X or Y equals true if either X or Y or both of them are true. If they're both false, the answer will be false. The third one of these is negation, which or often just not. And this just means X not 1 means that X was 0. Or the other way around. We're going to dive into these into more detail in terms of what they would look like in terms of actual logic, or if you were building electronics or within computer science, something like that. And we'll be talking about some of the notation used to describe how these things are connected, because this is going to matter later on. First of all, when we're talking about actually kind of building circuits that contain these concepts, what we usually end up describing these operators as is what's called a gate. Now, there's going to be a gate for each of these, which is of course your conjunction AND gate, your disjunction OR gate, and your negation NOT gate. Now we'll be talking about these specifically in terms of how to analyze their inputs and outputs, how those things are described, and then some basics about how those things are combined. But this will of course be something we'll go into in greater detail in the following video. So first of all, looking at this from the perspective of the conjunction, the AND gate. That gate is denoted this way when you actually see it show up in like a circuit diagram somewhere where someone's describing logic. Whether that's actually a physical circuit or just a logical connection, you'll see that in the same way. It shows how things are connected. It allows a common dialect for how to describe what is going on. Now, within that gate, we also have what's called a truth chart, which describes how different inputs provide different outputs. So that chart for an AND gate looks like this. As you can see, there's sort of the X and the Y going into it, and then the output is the X and Y, which is one of these numbers here. And you can see that in this case, it only produces true if both the inputs are true. Next up is the disjunction, or the OR gate. That is shown this way within a diagram. And its truth chart looks like this. Now as you can see, as I mentioned before, this one is true as long as either of the inputs is true. The final one of these basic gates that we can describe this way is of course the NOT gate. Now this one has a very basic truth chart, of course, this one here, where things just swap whatever they are. If they were true coming in, they're false going out, and the other way around. Now one of the things that's kind of commonly shows up regarding any of these is you also have a couple other sort of auxiliary gates that are pretty common, and it's worth mentioning them just so that you can see the pattern in how some of these things are described. For example, the AND gate itself has a gate which is the complete opposite, which is a NAND gate. So it looks like this, and you can see all that's done to it is this little circle's added after it, kind of like that circle in the NOT gate. And that's basically how that works, is whenever you add that circle to something, it essentially means to negate it. The truth chart for this is, of course, the complete opposite of whatever the AND gate was. So when the AND gate looked like this, the NAND gate looks like this. It's basically the same as just having an AND followed by a NOT. Similarly, the OR gate has a similar NOR gate counterpart. And this is again the same thing. Adding this circle to it, it's essentially going to be negating whatever the result is. So the truth chart for an OR gate looks like this, but the NOR gate looks like this. Something else which is a common gate that people talk about a lot, and in fact it's worth knowing about because it comes up in, say, a lot of kinds of logic, but also in computer science there's usually operators that describe this because it's usually incredibly useful. It's also very easy to implement in hardware. So that gate is of course what's called the XOR gate. Now what this means is exclusive OR. So if you look at the truth chart, you can see it's kind of like if you combined the properties of OR and NAND. It's something like that. In fact, you can build them fairly easily out of a combination of other gates that way. But what it means is it's only true if one of the inputs is exclusively higher than the other one. So it's like an OR gate, except it's false if both inputs are high, or both inputs are true. So just to put that into specific detail, we can use the XOR gate to also show how to connect different other gates. So for example, this diagram here is actually a combination of other gates which give the same result, the same truth chart as the XOR gate. So this is how we actually, if you're going to build a complex piece of logic, this is how you would describe it. You'd show these lines connecting everything. That's how you can see where the inputs are moving and where the outputs are going and how you get your final result. Now, something else that's worth knowing about now that we're talking about how to put these things together, which is going to be the topic of the next video, but to begin with, just sort of an idea of how some of the basic rules behind this actually work, there's something called De Morgan's law. Now, De Morgan's law is, or De Morgan's laws, because there's actually a few that kind of work together, they essentially tell you how you can negate an entire system. If you have a combinational logic system, you can actually negate one part of it, and it shows you how to pass the negation through it to actually change everything to have the same answer, but potentially be simplified. So like in other forms of algebra, there's always this kind of concept of simplification, the way that you apply certain rules and certain operators to actually simplify expressions. Well, Boolean algebra has the same thing, and De Morgan's law is one of the most common examples of that. So specifically, if you were to negate a bunch of operations around an OR, De Morgan's law says, well, that's the same as this, if you negated them and made them negations of AND. So it's a way of actually kind of reversing things. Similarly, if you had that negations of AND, it shows how this is how you pass it through and kind of distribute that to become negations of OR. So it's sort of changing, well, is your negation on the inside or the outside of the expression, and how do you actually invert the operations to get that to be the same? Of course, one of the things anyone might be noticing if they have any background in things like set theory, for example, is that, yeah, these look very familiar. And they are. A lot of the operations within Boolean logic are very, very similar to what you get in set theory. For example, your AND, your conjunction, well, that's going to be the same thing as an intersection in set theory. So a Venn diagram like this. And of course, your disjunction is the same thing. It's very similar to a union, which looks like this. And your negation, well, that concept exists as well. It's just being able to negate a set in set theory, which looks like this. So these things are all very similar because, again, it's all just various forms of algebra. And so the kind of exchange of ideas across the different fields should not be surprising. In the next video, I'm going to be talking about how we actually put together Boolean logic expressions into what's called combinational logic, which is when you start actually building more complex statements using these simple underlying ideas. And there, of course, are other examples of how this shows up, other applications all over the place. So the basic one that we're going to talk about is electronic circuits. But there's also other things like search queries, search engines and SQL databases, things like that. These all have this idea that you can ask for something negated or something and or something else. In fact, in those statements, if it's meant to be, if it's more of a queried language as opposed to an algebraic language, usually it's actually written out as or, and, not, something like that. But these expressions exist there as well, and some search engines have expressed that, have exposed those capabilities before. I'm not sure if they still do, because they're kind of hit and miss anyway. And also, yeah, if you've tried to work in any actual query language, those things pretty well always have some concept like this. And they're very useful. And so it's how you start to think in actual formal logic of how you're describing data you're interacting with, or describing an operation on some piece of data or some inputs. So anyway, I hope that was useful. Again, this is kind of the first in a set of probably 3 videos that are going to be talking about how we build up toward building actual circuits and how your CPU actually executes them. Now, I'm not going to be going into it in incredibly fine detail because, of course, these things are really small and have a lot of parts to them. But in terms of the overall idea of how you'd actually perform the operation, how it's going to be generally looked at by the circuit, and what that means. These are things which will become clearer as we go through that. So anyway, let me know if you have any questions, and thanks a lot. Bye.